Okay, welcome to Lecture 7 of Data Mining at Google. I have up here to remind you about the midterm exam, which you don't care about, but that probably means that we won't have class next Friday, but I'll give you more details about that once I make a decision. There's another homework posted if you're interested in seeing sort of those problems, and I might go over some of the solutions next Tuesday. So basically the plan though is today to get through the rest of chapter 3. There's not too much left, just some summary statistics. And then I want to start getting into chapter 6, which is about association analysis, which is sort of one of the classical problems in data mining. So it'll be good to sort of get out of some basic stat stuff into some more classical data mining stuff. In fact, it's probably the two extremes, right? Because everything we've seen so far you probably could have in an elementary stats class. Everything about association rules you probably never see if you're coming from a stat background. So we sort of go from one extreme to the other. Okay, so you don't care about the midterm exam, you don't care about homework, but you do care about chapter 3. So we did visualization last time. In fact, actually we finished up all the visualization. So that left us with section 3.2, which was summary statistics. So I talked about this last time. So yeah, 3.2 is left. So I always said, we like to do visualization first, and then we do summary statistics after we've at least taken a look at the data. And so we're going to talk about different summary statistics. So the classic example I would give you, right? So visualization, you can make a scatter plot, right? But how many scatter plots can you really look at one time? Maybe you also want to just compute correlations, and then where you see large correlations, then you look at those scatter plots. So the two of these things work well together. Visualization gives you the whole picture, but if you're comfortable that you know what the data is doing, then you could first do some summary statistics, or maybe you do the summary statistics first just to pull out the ones with the largest correlation, then you look at the scatter plots. So those two things would go together, just like things like the mean and the median would correspond to looking at box plots. Maybe you don't want to look at a box plot for everything, maybe you want to pull out the means and medians first and then look at those box plots. So they sort of work together. I do encourage you to do visualization first though, if it's possible, if it's scalable. So your book talks about some sort of the classic measures of location, measures of spread, and measures of association. So, measures of location are basically where does the distribution live? If I'm trying to compare two sets of exam scores, for example, I might compare the two means. So one mean is higher than the other. I might compare the two medians. One median is higher than the other. I might compare the percentiles. I might say, oh, the 75th percentile, this distribution is higher than the 75th percentile, that distribution. And these are talked about on pages 100 through 101 of the book. And I'll just go through and say a little bit about those, but of course you're probably all familiar with those. Measures of spread. You've probably seen these before. You probably remember from some elementary stat class doing the standard deviation calculation. And if you want to see it, I'll go through sort of the calculation today, but it's pretty simple. And then finally, measures of association. We talk about covariance and then a rescaled version of that, which is correlation. So what does your book say about measures of location? Well, the one thing that's interesting is they don't group the percentiles with the mean and median, although arguably these are all measures of location. And the percentiles are not measures of center, right? Those could be measures of any part of the distribution, whereas mean and median are both measures of center. Some terminology that I should mention. This is probably intuitive, but I'll just say it. First, second, and third quartiles correspond to 25th, 50th, and 75th percentiles, respectively. So you'll hear sometimes we use these sort of interchangeably. The other thing that's sort of curious, someone asked me this one time, which is actually an intelligent question. They said, how do you differentiate if I say someone is in the fourth quartile? That means they're in the upper 25th percent of the data, but we also refer to the first, second, and third quartile as being the divisions. And that's true. And if you sort of think about the data, we'd say this is the first quartile, second quartile, third quartile, whereas the fourth quartile, there is none, right? Just like there's 4 quarters in the basketball games, but only 3 breaks between quarters, right? So the point I'm trying to say is we interchangeably refer to the division here as being the third quartile and this group here as being the third quartile. And you have to use the context to know what people are talking about. Usually if people say the first quartile, they mean the division between the first 25% and the second 25%. The second quartile is the division between this 25%, this 20%, and the third quartile is this division. But sometimes if someone says I'm in the third quartile, then they mean they're in this group of 25%. So the language is a little bit sloppy. And someone asked me one time for clarification on that, and I said, really, there is no clarification. It depends on whether you're saying I'm in the third quartile or this is the third quartile. But they use the terms interchangeably. Let's see, what else do I need to say on this slide? I think I don't need to say anything else on this slide. The one thing I will tell you about, though, is that if both the mean and median are used to measure center, which is better, when should I prefer one over the other? Well, the thing to appreciate is that they both measure center, but sometimes the median is preferred because sometimes the median is preferred over the mean because it's more robust to outliers or extreme observations and skewness. And the way to think about this is if you imagine starting with a symmetric distribution. So, I drew a nice symmetric distribution here at the bottom. It looks sort of like the normal distribution. You start with a symmetric distribution. Well, obviously for symmetric distribution, everything's symmetric. The mean and median are going to be equal. Doesn't matter which one you use. And when you see people reporting, one or the other only, it probably means it's not symmetric and there's some reason to differentiate. But for symmetric, they're both the same. Now you start adding take the largest guy here and add like 1,000,000 to him. Well, the median is still in the same place, right? It's still the middle number. But the mean is going to be influenced, right? Because the mean, you add up all the numbers and divide by the total. So if I take the largest guy and I add 1,000,000 to him, the median's going to stay put, but the mean's going to follow him out. And as you get something that's sort of like general right skewness, like that, that's what's called right skewed. And to me, I always looked at these and saw these backwards. This one always looked left to me, and this one always looked right to me. So I just had to figure out some way to remember it, because everyone uses this terminology. And this is the common one. I always remember this is the common one, and this one's called right skewed. Why is this one common? Because you see it all the time. You see it with incomes, right? Most people make a fair amount of money, but then there's a few really rich people. Why are there no really poor people? Well, you can't make less than 0, right? You see it with house prices. You see it with times, right? How long does it take someone to do something? It takes most people a reasonable amount of time, but then there's a few people that take a really long amount of time. And no one takes a really short amount of time because you can't take less than 0. So this type of data is called right skewed. And with this data, the median is going to be here. 50% is below it, 50% is above it, but the mean is going to sort of chase out with the large guys. So this is the median for the right skewed data, and this is the mean. So the point is that the mean is affected by the really large values, whereas the median isn't. And sometimes one fix people will use with this data is sometimes take like a log transform and make it more symmetric. But in general, you have this problem where the mean and the median are going to be different. And for that reason, people will often report the median with this data. And then, of course, the left skewed is the opposite case, where you have most of the data is here and a few really, really small observations. And an example I could give you on that is something like, I had this example of basketball players' free throw percentage. Most people shoot like 70, 80, or 90, but then you have a few people that are sort of like really bad. You don't have anyone who's super great because you can't get over 100%. So that would be an example of left skewed, and in that case, the mean is actually smaller than the median. And again, of course, if it's symmetric, it doesn't matter. And so what you'll see sometimes is you'll see people using the median because they don't want to be influenced by these extreme large or extreme small observations, or they don't want to be influenced by the outliers. And so like even here, this is just a random story that showed up in the news a couple of years ago. It says the San Francisco median home price tops 600,000. This is actually from 2005, I think, which is right when we moved here. So this will be in 10 years, right? This will be funny to put up here, I guess, hopefully. So the thing is, they take a risk when they report the median home price, because there's going to be people reading this this is MSNBC, right, a pretty general audience that have no idea what the word median means in this context. But no one is interested in talking about the mean home price going up by a lot, because the mean is going to be unstable, and it's largely going to be a function of whether or not the few really famous or really expensive homes happen to sell that year. So really, what you're interested in is the median home price, the price of the home, where 50% of the people have a cheaper home and 50% have a more expensive home, because you know that the house prices are going to be right skewed, and so you're really not interested in reporting the mean. So you go out of your way and report the median on something like that, because that's really what you're interested in. And I'm just curious if they explain it anywhere in there. No, they just say median price, right? So they just sort of hope that people know what it means. So that's, I think, all I wanted to say about that. The point is that when you have right skewness or left skewness or outliers, it's often better to report the median because it's much more stable. And you can take the top 50% of your data and add 1,000,000 to it, and you're not going to change the median, but the mean would change a lot. And that's really important when you even, not just outliers, but you have like bogus data sitting in there. It's not going to be affected by that. Okay, so that's all I wanted to say about mean, median. Any questions, comments on mean versus median? Question?
So I believe the only real reason to ever use the mean is that sometimes it's so much easier to compute because you know the total and the number of people in the population. Like you have the GDP and you know how many people live in America, you automatically know the average income. It's not very useful, but it's very easy to compute.
Right, so the common is, one reason for using the mean is it's easy to compute, because if you know the total and you know how many people you have it, and it's also computationally more efficient. Am I saying all you guys know this better than I do? But that's true, right? I mean, the median involves sorting a list, whereas the mean I just have to average.
Well, there's an ON algorithm for the median.
There's an ON algorithm for the median?
I can show you.
Okay, so I'm wrong. But anyway, it's easier for me to compute the mean, it's just average numbers. The other thing to say, though, an argument for the mean over the median is the following, right? So we're talking bad about the mean. So it's the following. If the data is symmetric, right, then they're the same thing. Okay, if the data is symmetric, they're the same thing. So you're trying to get the same number either case. It turns out the mean is actually more efficient statistically. So we're talking about how the algorithm scales. If you talk about how your sampling error scales, it scales at the same rate, but the constant is smaller for the mean. And you can show that if you sort of do the stats. And so there is argument. If they're the same thing, you're better off to use the mean. It's more efficient statistically. But if they're not the same, the median tends to be preferable just because it's not influenced as much. Okay, any other comments on that? Okay. So measures of spread, right? How do we measure how much spread there is to a distribution quantitatively? Well, the naive thing would be the range, which is the max minus the min. Of course, you don't want to use that because that's going to be extremely sensitive to outliers. Of course, it depends on two values, right? The largest and the smallest, both of which could be outliers, so that might be useless. And if you get a lot of data, either the range blows up or the range is 1 because the data lives on 0 to 1. It's just not that useful. Variance and standard deviation are the two most common measures that you'll see. Usually standard deviation, which is just the square root of the variance. So I asked this on an interview question the other day, what's the formula for variance? And they didn't get it right, so I don't think it's too trivial then. Well, we didn't hire them, I guess. So, but it's like not too trivial to write this on the board and maybe do one example. Basically, you're just taking each number, right, subtracting the mean. Okay, how far is each thing from the mean? That's going to be a sign distance, so you square it. That becomes positive. You add it up, and then you divide by n minus 1. Why not n? Well, it doesn't really make a big difference. This is sort of, again, some theoretical property that makes it what we call unbiased, but you can imagine it doesn't really change things too much whether you use n or n minus 1, and you'll see some people use one or the other. So this is the variance, and then the standard deviation is simply the square root of that. Now, this is the most common measure of spread. People report the mean and the standard deviation. Of course, the problem with this is that it's very sensitive to outliers. If you get a really large or really small number, it's going to be really far from the mean. When you square it, that has an even bigger impact. So this is very sensitive to outliers. So you'll see people do modifications of this to make it less sensitive. One real simple thing people will use is what's called the interquartile range, which is basically just, people will call this IQR, interquartile range, just the third quartile minus the first quartile. And this is a nice, robust measure of spread because you can add something to the top 25% or the bottom 25%, and it won't, 50% of your data could be corrupt, and this, as long as the middle 50% is right, that's what this is computing, right? It's, if you think about the box plot from before, basically this is the distance from Q3 to Q1. It's the how wide is the middle 50% of your data. So that's a nice way. And if you remember, the outlier algorithm in R actually uses this value to detect outliers because it's a nice, robust measure of spread. But that being said, the variance and the standard deviation are the most common. Now you say, when do I use variance? When do I use standard deviation? Standard deviation, which is the square root of the variance, is the preferred thing because it's on the scale of the original data, right? If your data is in minutes, variance is squared minutes, whereas standard deviation is back in minutes. So standard deviation is preferred. However, the variance is nice because sometimes you can add variances, right? If things are independent, the variance of the sum is the sum of the variance, whereas that's not true with standard deviation. So sometimes you want to use one or the other, but generally standard deviation is the one you report because it's on the scale of the original data. So I think I said everything I wanted to say on this slide. Any comments about any of these guys? So let me just do a simple calculation here. This sort of might be insulting to you, but I'm going to do it anyway, so you have to be insulted. It just says compute the standard deviation for these numbers. So the standard deviation, here I just erased it, but again, you just take each number, subtract the mean, square it, add it up, divide by n minus 1, and take the square root. So these guys would be 210, 210, 22, 43, 18. Okay, so those are your x's. Those are your numbers. From these guys, 4, 7, 15, no, sorry. what's that? 4, 7, 15, carry the 1. That's right, 4, 95. So my mean is simply 95 over 5, which is 19, right? Okay, so from each one of these, I'm going to subtract 19. So this is negative 17, this is negative 9, this is positive 3, this is 24, this is negative 1. Okay, then I just square each of those guys. This is, what's 17 squared? You don't know. 81, 9. What's 24 squared? We don't know. Wait, 24 is what? 496? What's 17 squared?
Oh, for 7.
2. Wait, what? What's 17 squared? 289. What's 24 squared? 496? 496. Okay, we'll see. Let's see, 10, 10, 16, carry the 2, right? 10, 18, hang on. There's 10, 26, carry the 2. 18 and 9 is 27, carry the 2. That doesn't look right. 5. 5. What's wrong? 496 is, you guys. I give up. I thought this was, here we go. Technology. Okay. Work. There we go. 17 times 17. 289, that's right. 496. 24 times 24. 576. 576. All right. 576. Okay, 10, 20, 26, carry the 2. 18 and 7 is 25, carry the 2. 956, does that look right? 956 over 4. Let's try that. 956 over 4, 239. So 239 is your variance. And you see what I'm saying about it being sort of not sensitive to outliers, right? The 576 sort of dominates the calculation because of the one large number. So it's not very sensitive to outliers. Something like the interquartile range is more stable, more robust to outliers. Anyway, variance is 239. Question asked for standard deviation. So it's simply square root of 239, square root of 239, which is something like 15, I think. Where's the sun? There it is. 239 square root. 15.46. Okay. And if you do it once, then you never have to do it again. If you were doing this in something like R, you could just get these guys here and read them in. And there's a SD function, right? So this is data, store as, I need commas, say 2, 10, 22, 43, 18. And I say SD of data, oops, caps lock is right there, data. And it says 15.46, right? And if you don't believe that, you can see the variance is the square root of 239, which is what we got after we got our arithmetic straight. So that's this calculation that you probably remember from elementary stats class. And you can check the same value in Excel. In Excel, it's STDEV that gives the standard deviation and VAR that gives the variance. Okay, so I think that's all I want to say about measures of spread. Any questions about measures of spread? Question?
I was kind of taught that standard deviation was only really supposed to be applied when you had a reason to believe the distribution was normal in some way.
Yes.
I haven't really been sure of that. Is that?
Well, so the comment is, whether a standard deviation makes sense if the distribution isn't normal. People use it all the time. And even, you could argue even for like a discrete distribution with, binary, arguably it makes sense, right? I mean, people talk about the standard deviation of the binomial distribution, right? Which, so that's discrete distribution, doesn't look at all symmetric or anything like that. I think the thing that you want to watch out for, though, is that, like, if you're comparing two distributions and this one is sort of like this, and then this one is sort of like a point mass, but then it has like some really large values. And you say, like, which one has a bigger spread? Well, the second one is going to wind up, having a few large values blowing up the standard deviation because of that square and things like that. Whereas the first one, arguably, if you look at maybe the IQR, the first one is larger. So it's okay to apply the standard deviation. You just have to be careful that it is sensitive to outliers. And if you have one or two really large values, it can blow it up because you're taking the squared in. Some people will, get rid of the square and just take an absolute value here and do like an L1 measure, which is also more robust. So there's more robust measures, and I think that's the concern that people might tell you. Be careful if it's an unbounded support and there's some really large outliers, you should be careful about it. Okay, other comments about standard deviation or variance or any of these measures of range? Okay, so, last thing to talk about is correlation and covariance. These are measures of association. So if I have two numeric variables, the question is, how strong is the association between them? Now, of all these, I think this is the one you probably have to be the most careful about outliers, and I'll show you some pictures of what can happen with these. Just beware of anyone who says, oh, the correlation was 0.999, right? It could be because of 1 point, and I'll show you why. So basically, both of these measure the strength of the linear relationship between two numeric attributes, x and y. And the way it works is you take each number, right, for x and subtract the mean, take each number for y and subtract the mean, and take the product, right? So you're just recentering them at their mean. So imagine their mean is 0, and then you're taking this multiple. So when am I going to get a big correlation? I'm going to get a big positive correlation if when x is positive, y is also positive, and when x is negative, y is also negative. Excuse me, because then the product will always be a big positive number, right? So this will be the positive linear relationship that you're thinking of. That's going to correspond to a positive value for the covariance up at the top. And likewise, when is it going to be negative? Well, when x is negative if y is positive, right? So it's basically looking for positive would mean they agree in sign, negative would mean they disagree in sign, and then the magnitude corresponds to how strong it is. Now, the magnitude of the covariance is not that meaningful because you don't really know what scale this number lives on. So what's often, I'd say like 90% of the time, reported at least, is the correlation, which is a rescaled version of this, which is sometimes denoted R. And so this up here that I wrote down, this is the covariance. The correlation is simply the covariance rescaled by the standard deviation for x times the standard deviation for y. And so I said here, correlation is covariance divided by the product of the two standard deviations. And this has the nice property that it rescales it to live on -1 to 1. So this thing here lives on -1 to 1. And then sort of the absolute numbers become meaningful. If someone says, I found the correlation to be 0.9, or I found the correlation to be -0.8, you sort of know what that means. And even if you don't, you can relatively compare two things that are on different scales by looking at their correlation. Say the correlation between intelligence and time to complete the task was this, but the correlation between intelligence and income was this. Even though all the variables are measured on different scales, you've measured the strength of the linear relationship with the correlation, which lives on -1 to 1. Again, it's often denoted by R. Sometimes it's called the coefficient of correlation. Now, what I was saying is that both of these are very sensitive to outliers, and let me sort of show you why that's the case. So whenever someone reports a high value of correlation, you should be careful of it. And also, you should also note that these are not invariant to monotone transformations. So it depends a lot how you measure the things. When someone says intelligence is correlated with income, well, it depends sort of how you measured intelligence, right? If you took the log of intelligence, the correlation would change. So what is intelligence? It's not, it's a qualitative thing. It's not really a quantitative thing. Okay, but that aside, how are these sensitive to outliers? So suppose I have data, right? No relationship at all. Okay, just no relationship at all between x and y. That's my data. No relationship at all, correlation should be about 0. However, if I add one guy right here, correlation would be like 0.999, right? Just 1 point can drive the correlation. And that happens, right? Because if you happen to get some really large x outlier and he's a really large y outlier, 1 point can drive the correlation. And so what'll drive people crazy is like one day they'll have data like this, that looks like a huge correlation. And the next day, they'll have data like this that actually does show a nice pattern, but that big guy is gone, and that actually has lower correlation. So the correlation can be really influenced by 1 point. And it can also actually like reverse the correlation, right? If you have something that's, let's say like you have a strong negative correlation in your data, okay? But then you get 1 point right, so this would be, right, this would be a strong negative correlation. But then as soon as you get 1 point right here, it's going to go the other way. It's going to look like it's positive. So there's a relationship between the correlation and simple least squares regression, which is when you have the simple least squares regression, you have r squared. This r is exactly the square root of r squared. Now, when you have multiple variables, r squared still makes sense if you designate one to be your response, but correlation is necessarily between two predictors. So anyway, people always love to report correlations, right? The correlation between this and this is really high, so I found a strong relationship. Okay, but if it's just two attributes, right, so you should probably look at a scatter plot and make sure that it's not just a few strange observations that are influencing things. And of course, again, we talked about before, the correlation does not imply the causation. It merely implies the linear relationship. Also, it doesn't measure nonlinear relationships, right? If you throw the ball up in the air and record how long it takes to come down, you get a parabola, correlation is 0, right? There's no linear relationship. The least squares line goes right through that. Okay, I think that's all I wanted to say on this slide. Any comments on this slide? Okay, so here's the story, right? If the slope of the least squares line determines the sign only, right? So if the line is going up, it's positive. If the line is going down, it's negative, right? So both of these have negative correlation, both of these have positive correlation. Slope determines the sign. How close the points are to the line determines the magnitude. The closer the points are to the line, the closer it is to -1 or +1. So this is -0.6 because the points are pretty close to the line. This is +0.3 because the points are pretty spread out. The slope doesn't determine the magnitude. The slope only determines the sign. How close the points are to the line determines the magnitude. So sort of as an exercise to sort of get that, here I did kind of a multiple choice, match the correlation to the picture. And these are all correct. I actually computed these 5 correlations for each one of these pictures. And I have them labeled as A, B, C, D, and E. And then I give some possible values, some possible choices. And so right off the bat, right, you can throw out -3.20 and +1.20, right? Because the correlation is always living on -1 to 1. So those aren't even there. And then I have, I guess, 1, 2, 3 negative guys and 2 positive guys. So we can do the 2 positive guys first. So those must be A and B. And if you compare A and B, arguably in A, the points are closer to the least squares regression line than they are in B. So A must be a picture of 0.86, and B must be a picture of 0.95. So if you want to know what is 0.86 correlation. What? Oh, yeah, they are. Well, when you get really close, you can't see. Sorry. Did I say it backwards, too? I don't remember what I said. So A, they're closer to the line. B, they're further from the line. Okay. So what was I going to say? So if you want to know what a picture of 0.86 looks like, there it is. If you want to know what a picture of 0.95 looks like, there it is. Of course, like I said, 0.95 can also look like a whole cluster of points and then 1 up there, too. But if things are good and there really is a linear relationship, this is a 0.95 strength, this is a 0.86 strength. Okay, so then that leaves the negative guys, C, D, and E. They're all negative. Now, the strongest one is actually C. Even though the slope is not as steep as the other slopes, I mean, you probably can't even see the scale, which of course would be relevant, but it doesn't matter the slope, it matters how close the points are to line. So C is the strongest one, so that becomes -0.98, which is the smallest number up here, 0.98. And then D, right, this is the most spread out from the line, so that's got to be the -0.40. And then E is the middle one. E is a picture of -0.96. They're still pretty close to the line, but not as close as the -0.98. Okay, so this, the correlation on an absolute scale isn't that meaningful to you until you see a lot of examples, but, here's 5 examples that you've seen. And then even if it still doesn't really, you always forget on an absolute scale what it means, still the relative values are important, right? If I say the correlation between exam 1 and exam 2 is 0.9, but the correlation between exam 2 and exam 3 was only 0.7, then somehow those 2 exams are more different than exam 1 and 2. Okay, that's that. Here's an interesting thing to do. If I generate 1,000,000 numbers from the uniform distribution in R and call it X, and I do the same thing again and call it Y, what should the correlation between these be? 0, right? There should be no linear relationship between these. So you can check correlation between x and y, and of course it's very close to your 0. And if you did more, you would get it even closer to 0, right? Because the random number generator is generating these things supposedly independently, and so there should be no relationship at all, and that includes no linear relationship, right? And you can sort of converge to your machine 0 if you keep bumping up your sample size. And of course, if you were to plot these, well, actually, you can get in trouble if you plot these, because I told you about scatter plots don't really work when the data is too big, right? Because you just basically color in the whole picture. So this would be a case where you'd want to sample. But believe me, there's no linear relationship between these, right? you can sort of bump it down a little bit and see that, right? With 1,000, you should be able to see. There you go, right? No linear relationship at all, which is what you want from a random number generator, right? You don't want. But I have heard like people get into trouble with these things when you get into high dimensions. They can wind up living on hyperplanes and that if you don't do things right. Okay, so that was 24. This question says, what value of R would you expect for the 2 exam scores which are plotted below? I should have put a question mark there. Compute the value and check your intuition. So who says 0.7? Who says 0.8? Who says 0.9? 0.9s are closest. It's actually 0.89 on this one. Okay, that's don't be fooled though. That line is not the least squares line. It's the diagonal line we drew before. Now, if you want to, if you don't believe me, why the 0.9 people won on this one, you can take a look at this. It's cute, sort of, that Excel does not complain and R does complain, and I'll just mention that. So insert function CORREL in Excel does the trick. What if I give it these two? Does it complain? Yeah, it probably doesn't like that. Okay, so what if I give it this one and then this one? Does it? No, it doesn't like that either. Okay, so it's bothered by the fact that those names are there. So I'll just give it these guys and then give it these guys. And it should compute the right value. Let's see. There we go, positive 0.89. So we'll round it off to 0.90, unless you thought it was closest without going over, then the 0.81s. Okay, if you do the same thing in R, it doesn't like it, right? So let me change, let's see. Where is a file? No, that's the thing. File, change directory. Where do I have this thing? Somewhere. Well, let me put it on my desktop, then it'll be on my desktop. Okay, let's see. Where is this data set? It's right here. So put it on my desktop. And the reason R is going to complain, well, I'll just show you. So let's see. Say data, store as read.csv. This is called exams and names.csv. And header equals true by default. Okay, so that's good. So you can see the data here. Looks good. Okay, so I'm going to say in R the function is COR for correlation. And I'll say, let's see, data column 2 with data column 3. Oops. And remember, plot did not complain, but correlation does complain, right? Missing observations is an error, whereas in plot it wasn't even a warning. So you get different behavior for different functions in R based on the missing data. In this one, the fix is something different than it is in other things. Sometimes there's this na.rm, which is very common. In correlation, though, it's use equals all observations is the default, when in fact you would want to have use equals complete observations to get it to not complain. So correlation use equals complete dot observations. There you go, same value as Excel. So default behavior there is to complain and give you an error. Sometimes the default is to give you a warning. Sometimes it's to not do anything. So it's interesting to note the different behavior for missing values. Probably, it's open source, so it probably depends on who wrote the function the first time. And then after that, it's stuck. Okay, so that's that. Question?
When you're doing complete observations, is it not included in the mean, or just not included in the calculation?
I think that's a good question. So the point is that if the pair has one missing, you can't compute the product, but you can still compute the mean. And I think On that one, what it's doing is it's ignoring it for the mean also. But you can read the documentation on that because, that's the point with missing data. Sometimes you can still compute some of the statistics, and I'm not too sure what R does. Anyone know off the top of their head? I think it just ignores everything that has at least one of them missing. But both approaches have been suggested. Okay, so I think that's all I want to say about Chapter 3. Any last comments, questions on Chapter 3? Okay, so like I said, we're going from one extreme to the other. Chapter 2 and 3, arguably you could get these things in a basic stat class. Chapter 6, association analysis, you kind of have to take a data mining class or something fairly modern to see this type of thing. And I'm not going to get into it too heavily. I really kind of want to introduce the type of data that motivates this problem. And I want to show you one formulation of the problem, which has a lot of drawbacks to it, but it's probably the first formulation of the problem, and it's the one that your textbook sort of gets into the most, but it's a simple formulation of the problem. It's, you'll see what it is, but it's not the most obvious, and it's probably not the best. So what's going on with association analysis? Basically, it's coming from the supermarket data, right? The classic data mining example, that all these people buy things at my supermarket, maybe I can learn something from them. So it uses a set of transactions to discover rules that indicate the likely occurrence of an item based on the occurrences of other items. So for example, if I know someone bought diapers, does that mean that they're more likely to buy beer? If someone bought milk and bread, and I shouldn't even say more likely, I'm already saying too much. If someone bought diapers, does that mean they're likely to buy beer? Okay, and that's actually more likely versus likely is an important distinction, but we're just saying, if someone bought diapers, does that mean they're likely to buy beer? If someone bought milk and bread, does that mean they're likely to buy eggs and Coke? If someone bought beer and bread, does that mean they're likely to buy milk? So these would be examples of association rules, and we can sort of quantify the strength of these rules, and I'll show you a couple metrics for doing that. The important thing here, again, implication means co-occurrence, not causality. Now, you hear a lot of people badmouth, these things. So this is just, co-occurrence. This is just correlation. It's not causality. But it's important to think. I mean, in some cases, that's okay, right? Like when my insurance company charges me more money to drive because I'm a male versus I'm a female, okay? They're not saying that being a male causes me to drive fast. They're just look at their data. The males get in more accidents. We're going to charge them more, okay? It doesn't really matter what the causation is. In fact, the causation question doesn't even make sense there, right? Because if you ask the question of causation, you have to say, well, what would be the natural experiment to refute that? Well, they would have to say, take everyone who's a male now, change a random portion of them into females, and see if they get a more. It doesn't even make sense, right? There's too many other things that are correlated with it that you can't even really isolate the causation question. But just the point of this last bullet is that we're not really looking for causation. We're not even trying to infer the reason. Oh, maybe they have, a baby and then they like to drink. You're not trying to do that. You're just trying to look for the strong association. And just, it's a descriptive exercise. What's in your data? What associations exist in your data? So there's a whole bunch of definitions up here. This morning when I went through this, I wrote all these down, but I think, I don't need to, and we only have 20 minutes, so I'm not going to write them all down. But they're important, even though I don't want to write them down, they're up here. So the book talks about item set. Now, the book is really sloppy. It's always borrowing notation from set theory whenever it's convenient, but it's not very formal about it. So you sort of have to be forgiving of that, and I'll probably be equally sloppy. So an item set, they're making it look like a set, but it's basically a collection of one or more items. So this is kind of like a market basket, right? Like milk, bread, and diaper would be an example of an item set, and a K item set simply means it's a set that contains K, and let's say unique items probably. Okay, support count, which is different from support. Usually we'll just say what is the support, but they're going to start with support count, which is the frequency of occurrence, okay? So for example, the support count for the item set milk, bread, diaper is 2, because if you look in this data, you see milk, bread, diaper 1, milk, bread, diaper 2, and then there's no bread here, there's no milk here, and there's no diapers here. So only 2. So 2 is the support count. The 2 out of the 5 total is what we call the support. And that's usually what we refer to. The support of the item set milk, bread, diaper is 2 out of 5 because 2/5 of the transactions included a purchase of all 3 of those items. So that's the support of milk, bread, diaper. And that's probably the most important definition up here. So when we say support, just what fraction of the item sets contained those items, milk, bread, and diaper. And then frequent item set, sometimes we're looking for item sets who have support greater than or equal to some minimum support threshold. Okay, so if I were looking for all item sets that had support greater than or equal to 0.4, I would include this one as one of the frequent item sets. So frequent, of course, is determined by our threshold. Okay, another definition that didn't fit on that slide is what is an association rule. So they write it as, X implies Y, right? Write it like an implication. So for example, one item set implies another. Milk diaper implies beer. That's what it is. X and Y are both item sets, and you write it as one implies another. That's what an association rule is. Okay, how do we evaluate association rules? Well, there's two metrics that your book uses, and they use these in conjunction with each other. One is the support, and the other is the confidence. Now, you can argue a lot about both of these and say that they're not really the right thing I want to measure. You can come up with other metrics that might be more meaningful. It depends a little bit on the application, and I'll spend some time on Friday criticizing these. But this is the formulation that your book starts with in section 6.1, and so I'll sort of go through it, and then we can sort of criticize it later. So support, basically fractions of transactions that contain both X and Y. So the association rule, starts off like this, right? X implies Y. But when you're figuring out the support of X and Y, you sort of ignore the arrow, right? So for the example here, milk diaper implies beer. So let's go with that example. Milk, comma, diaper implies that I buy beer. Okay, oops, beer. The support of the association rule. So the previous slide defined the support of the item set. This is the support of the association rule. The support of the association rule ignores where the arrow is. It just takes everything and puts it together. Take milk, diaper, and beer and put it together. So the support, I guess I'll write here, the support of this association rule is nothing more than the support of the item set. I'll just keep them in order. Beer, milk, diaper. Okay, so what is that? How many transactions contain beer, milk, diaper? Let's see. Not that one. This one does. 1, 2, 2. Those two, right? So these two. Beer, milk, diaper. So this is 2 out of 5. Okay, so that is the support of the association rule, is simply the support of all items on both sides. Okay, 2 out of 5. Now, why do I want an association rule to have large support? Well, even if it has strong confidence, which I'll define in a second, you still want to know that these items are occurring frequently together. So 2/5 of the transactions involved a purchase of milk, beer, and diapers. Okay, that's all the support of the association rule is. Okay, the other thing to talk about, the other metric, is the confidence of the association rule. So the confidence of the rule, milk diaper implies beer, milk diaper implies beer, the confidence of the association rule is simply the following, right? Of all the people that bought milk and diapers, how many of those people also bought beer? That's what it is. Of all the people that got what's on the left side, how many people also got what's on the right side? So this you could define, let me move this here, so I know I'm probably not in the right spot. Okay, whatever. Let's see, this would be, on the top I would put the support of milk, diaper, and beer. How many item sets contain milk, diaper, and beer? And on the bottom, I would put the support of just the milk and the diaper. Milk, diaper. Okay. So then the top, okay, milk, diaper, beer, that's exactly this number. The top is exactly the 2/5. But the bottom is how many people bought milk and diaper. Well, how many people bought milk and diaper? 1, 2, 3, no milk, no diaper, 3. So the bottom is 3/5. And so you notice your book, I use support, they use support count. It doesn't matter because the denominator is the same. It comes out to be 2/3. So that is what we call, the 2/3 is what we call the confidence of the rule. And what that means is that among the people that bought milk and diapers, 2/3 of them also bought beer. That's sort of the strength of the implication. That's the confidence of the rule. Okay, of all the people that bought milk and diaper, 2/3 also bought beer. If I know you bought milk and diapers, there's a 67% chance you also bought beer. That's the confidence. That really tells you how strong the rule is. The support just tells you sort of how frequent this thing is, right? Because even if this were 100%, if it only happened like, one time in the data set, then it doesn't have much support. It's kind of like, the coverage. How popular are these items co-occurring together? So these are sort of the two metrics that your book talks about as measuring association rules. You can talk about a lot of other ones, and there's a lot of drawbacks to these. In particular, there's actually a problem with the confidence that you can probably see coming, is that you're really not comparing it to a baseline, right? So you say, like, if I bought milk and diaper, there's a 67% chance I also bought beer, but the curious question is, well, what's the chance you bought beer anyway, right? It's not being compared to a baseline. So that's one problem with confidence. So anyway, we'll talk a little bit more about that next time, but this is sort of the definitions of support and confidence. And to sort of make these more clear, I have an example question.
Yeah, it looks an awful lot like conditional probability.
Yeah.
So why not just
Yeah,
do that?
they do that too, right? So this is sort of like, something that lives outside of statistics, kind of reinvents conditional probability with new notation. And the notation is actually kind of backwards from the notation from conditional probability, right? Because you have like A implies B is really B given A and things like that. So it is basically, this is a conditional probability, right? This is the probability that I bought beer given I bought milk and diaper, right? So it is a conditional probability. And then you might want to compare that to the marginal probability and see if it's an increase or a decrease. So you're right, we are really working with conditional probabilities. It's different notation, and sort of we're not acknowledging that. And if you look in the book in section 6.7, they go through a whole bunch of other metrics, and they get into some probability-based ones and just sort of do metrics that compare probabilities. Okay, so let me give one example here. So this again is, I stole this one from one of the exercises, but I changed some of the letters. So it says compute the support for these item sets A, BD, and ABD by treating each transaction ID as a market basket. So there is a question, right? Do you want to treat the customers as the market basket, or do you want to treat the transaction ID as a market basket? And both of them might be meaningful, right? If you're trying to do discover rules at the customer level, then you might want to collapse and use customers. So, combine these guys into one, combine these guys into one. But if you want to do it at the transaction level, then you look and you say, oh, these are 10 unique transactions, so I'm going to treat each one separately and sort of make the denominator 10 and not acknowledge the fact that I actually know that the first two guys are the same customer because they have the same Safeway card, right? So this one says just use each transaction ID as the market basket. So we'll do that. So let's see, support for each item set is simply the count divided by the total. So support for item set A, how many things have A? 1, 2, 3, 4, 5, 6, 7. So support for item set A is 7 out of 10. Support for item set BD, let's see, 1, 2, 2. So BD, and you notice my notation is sloppy here. I'm not using the brackets or anything. 2 out of 10. And then as they get bigger, it can only get smaller, right? And now it's like the intersection in probability, right? As you keep intersecting sets, they get smaller. So ABD has to be a subset of these BDs, and so ABD is here, the 1 out of 10, right? Because the other BD doesn't have A. So that's 1 out of 10. So those are the support for the item sets, right? Those aren't association rules, they're support for item sets. And then we can use those numbers to calculate the following association rules. Calculate the confidence and support for the following association rules. BD implies A, and A implies BD. So if we do that, this is number 27, the support for BD implies A, right? The support for that association rule is simply the support for the item set ABD, right? That's what it is. And we already figured that out. That's 1 out of 10. Okay, so again, the support for the association rule is just the support for the item set that contains the items on both sides. Okay, and then the confidence for the association rule, BD implies A. On the top, it's the support of ABD, so that number 1 out of 10. And on the bottom, it's how many people bought B and D. So it's the support for BD. Okay, so on the top is 1 out of 10. how many people bought BD? 2 out of 10. So this rule has confidence 50%. 2 out of 10 equals 0.5. What does the 50% mean? And I actually asked that here. I said, state what these values mean in plain English. So in plain English, I would say something like 50% of the people that bought B and D also bought A. Okay, so you say if someone buys B and D, you're 50% confident that they're also going to buy A. Okay, how many of the transactions is this relevant to? This is relevant to 10% of the transactions where someone actually did buy all 3 of these things. That's called the support. The letter number is called the confidence. And then you can do the same thing with the other rule, which is A implies BD. So the support for A implies BD. Well, that's just going to be the support of A, B, D again. And so, of course, it's the same support, 1 out of 10. Right? It doesn't matter where the arrow is or what order they come in. The support is basically how many transactions have all 3 things, which is still 1 out of 10. However, you should ask yourself, is the confidence going to be symmetric? And of course, it's not going to be, right? Because this is A now implies BD. And so on the top, I got to put the support of ABD again. The numerator is the same, but now the denominator is the support of A. So now I have 1 out of 10 on top, and A is 7 out of 10 on the bottom. So this becomes 1 out of 7. 1 out of 7 is the support. So they both had, 1 out of 10 is the confidence. 1 out of 7 is the confidence. They both had, I'm ahead of myself, they both had support 1 out of 10, right? Because they both involve ABD. So they both have support 1 out of 10. But the first rule has 50% confidence, and the second rule, the confidence is only 1 out of 7, which means that of all the people that bought A, only 1 out of 7 of those bought B and D also. And actually, I shouldn't say people, right? Because we're doing it at the transaction level, not at the person level. So I should say, of all the transactions that bought A, 1 out of 7 of those also bought B and D. That's what this 1 out of 7 means for the confidence. Okay, so the first sort of problem formulation that people came at this one with, that's discussed in your book, is basically give me all of the association rules, and there's a lot of association rules, right? You can see how that thing is going to scale really, really poorly with the number of items. Give me all the association rules that have a support above a certain threshold and a confidence above a certain threshold. And I'm going to look at those as possibly interesting things. Okay, so you see the problem formulation, it's not a predictive task, it's just a descriptive task. I'm just looking to see if I see interesting relationships. And so this is sort of the first problem formulation that's discussed in the book. I'll go through a few more examples of it, but there's sort of more intelligent problem formulations you can make. In particular, this problem with confidence is like, so the confidence is high, but how much higher is it, if I didn't know that they bought A? Okay, so you can talk about that. I think that probably, yeah, we're up to 5 minutes. So I think I'll probably stop there and do the next few examples next time. And next time I'll also talk about sort of other problem formulations, difficulties with this formulation, and I'll also talk about what they call Simpson's paradox, which isn't really a paradox so much as it is a problem with not formulating your question clearly. Any questions before we take off? Okay, so I'll see you on Friday and we'll finish up chapter 6.